All right, guys, we're picking up on slide 22 of the chapter 6 PowerPoint. We're talking about electrons and the energy levels that electrons can exist in. Again, each energy level that we talk about for an electron describes if an electron is orbiting the nucleus, there's a certain amount of energy that the electron has to maintain if it wants to stay in that orbit. So there's a relationship between these orbits that there are certain orbits that are allowed, and an electron can shift from one allowed orbit to another allowed orbit. If it goes up, it absorbs energy. If it comes down, it emits energy. So based on those differences, we actually, in the late 1800s, early 1900s, a couple of equations were derived that allow us to calculate, first of all, this equation allows us to calculate the difference in energy between two allowed orbits in a hydrogen atom. Now specifically, these calculations are set up for a hydrogen atom. If we get to atoms that have multiple electrons, the math changes and becomes a little bit more difficult. I think some of those have been described, but for this class, we're just going to stick with hydrogen. So if I have the first allowed energy level, the second allowed energy level, the third allowed energy level, and then the fourth, fifth, sixth, again, notice that as you go up, they get closer and closer to each other. But the colored arrows actually show us the difference in energy, because again, going up is increasing energy. So if an electron goes from the first energy level to the second energy level, there's a specific amount of energy that had to be absorbed. And then if the electron drops back down, it's going to emit a photon that has that amount of energy, which if it comes out as a photon of light, it's going to have a certain wavelength. And if the wavelength happens to be in the visible range, then we might see it. If the wavelength emitted is not in the visible range, then it still comes out, but we can't see it with our eyes. There's a lot of light that is traveling around us that we can't detect with our eyes. So there are several different things in this that we could pick up. First of all, the difference between the second energy level and the first energy level, it's a pretty big energy gap. It's actually big enough that any drop from a higher energy level to the first energy level is always going to be too much energy for our eyes to see. So any drop from 2 to 1 or from 3 to 1 or from 4 to 1, that gap down to 1 is so big, it's always going to be ultraviolet light, and we will never see those transitions with our eyes. If we have a light bulb filled with hydrogen gas, and we turn the light on, the only colors we're going to see are going to actually come from these blue lines right here, which will be if an electron, when it jumps up to a higher orbit, it can come all the way back down, or it can actually do smaller steps. So we can see the electron dropping from 3 to 2. We can see when it drops from 4 to 2, 5 to 2, and 6 to 2. A hydrogen lamp will give off 4 different colors. Now again, if we look at the lamp, we only see the overall color, but if we send that light through a prism, it would be separated into 4 distinct colors. Okay? Those 4 colors come from 3 to 2, 4 to 2, 5 to 2, and 6 to 2 are the transitions that correspond to those wavelengths of those colors. Okay? And then again, if we get into, let's say it drops from 4 to 3, 5 to 3, or 6 to 3, those gaps are small. They're actually too small for us to see, and if it has less energy than visible light, that's going to be infrared. Okay? So we can get different types of light being emitted. We're only going to be able to see visible light with our eyes, but we do have devices and tools that can detect other kinds of light that we can't see. So we can still measure those other amounts of light. We just can't see them with our eyes. So the equation that's here on this slide is the equation to calculate the change in energy between different energy levels of a hydrogen atom. Okay. Now, right in the front of the equation, HCr sub H, that's actually an H right there. Those 3 are all constants. You can combine those, and I believe that I had that equation on the whiteboard in the last couple of videos that I made. So that equation with these plugged in as one value was already presented, okay? And then the NF is the final energy level, which specifically needs to be the lower energy level, because what we're doing with this equation, we're calculating the energy emitted by an electron when it drops from a high energy level to a low energy level. In this equation, NF needs to be the lower level, NI needs to be the higher level, okay? Now, specifically, this one is not as big a deal because the change in energy could be absorbing or releasing. But when we go to the next slide, we have a similar equation that we call the Rydberg equation. This equation, we've done, again, some substitution, and we're now able to solve for the wavelength. If we want to know directly when an electron drops from the fourth energy level to the second energy level, what wavelength is emitted, this equation will allow us to calculate the wavelength. Okay, so there's two different equations. One of them is set up to calculate the change in energy. The other one is set up to calculate the wavelength. You pick which one to use based on the problem that you're solving. Okay, so now let's do a problem on the next slide. If I want to know the wavelength of light that's emitted from in a hydrogen atom when an electron drops from n equals 4 to n equals 2. Okay, so my two n values are given. I want the wavelength. At that point, I know that I want to use the second equation that was presented on the previous slide. 1 over the wavelength equals the Rydberg constant, that's R sub h. This value is on the formula sheet that's provided on the share class files or in D2L. And then my two n values. In this case, it's very important that the n values it's the lower n value first and then the higher n value second, specifically because if we do it that way, we're going to get a positive answer. And when we solve for a wavelength, wavelengths have to be positive. It's the distance between the crest of two peaks of the wave. It's a distance, it has to be a positive value. Okay, so if I plug all that in and set it up, you should, when you solve this expression, notice that the equation is not set up to be equal to the wavelength. It's actually 1 over the wavelength. So when I solve everything on the right side, this is not yet my answer. 1 over the wavelength equals this number. And then the Rydberg constant does have units on it. It should be meters to the minus 1. So basically this is the distance, meters to the minus 1. So basically this is the inverse of the distance. In order to get the wavelength, I have to flip this side over, which means I need to do the reciprocal or inverse of this side. So my final answer is going to be 4.86 times 10 to the minus 7 meters, which again, we've learned you should know that the visible range is 400 to 700 nanometers. That is 4 times 10 to the minus 7 to 7 times 10 to the minus 7 in meters. Okay, so if I were you, I would like for you to know the wavelength range of the visible range in meters and in nanometers. So this is in meters, in nanometers it's 486. That does correspond, it is in the visible range. That wavelength would correspond to a specific color. I want to say that one's blue-green, but we can check that somewhere. All right, now, our equations and the Bohr model. You know, essentially Niels Bohr just came up with the idea that electrons are in these orbits. They'll never, once they're in an orbit, they'll never lose energy and fall into the nucleus. They can shift from one orbit to another, but there are only certain orbits that are allowed. All this theory that he came up with, it specifically applies to the hydrogen atom. When you start looking at other atoms, there are problems that can occur. It can create some issues and stuff. So pretty much for this class, we stay simple and we stick with the hydrogen atom. But this is all the foundation that allowed us to move into quantum theory. Quantum theory, which Schrodinger is the guy that came up with the cat in the box experiment, where you don't know if the cat's alive or dead. That's related to probability and all that kind of stuff. So our current atomic model, Electrons are in specific energy levels. We call them discrete energy levels. So they're specified and they are separated from each other, and there are only certain ones allowed. But the electrons, when they gain or lose energy, they can shift back and forth between the allowed energy levels. Now, a few more things. De Broglie is the guy that kind of said, okay, well, we know that light can be considered a wave or a particle, but then de Broglie said, well, actually, when you have really small particles like electrons, they're going to exhibit some characteristics of light also, or of waves, okay? So small particles exist as both waves and particles, so you could actually calculate the wavelength of an electron or the wavelength of a proton that is vibrating and moving at. So the de Broglie equation, the wavelength equals, it's actually h over m times v. Again, these are just kind of information and discoveries that helped us develop quantum theory to the level it is now. You don't really need to know much about what de Broglie did. It's kind of an interesting topic. Then also Heisenberg basically said whenever we study an electron or a small particle, you cannot find both the location and the direction that an electron is moving, because if you try to measure one of them, then just by observing and measuring it, you're going to change its path and its position. So that's called the Heisenberg uncertainty principle. And then Schrodinger finally came along, and he developed a lot of the math to derive wave functions and wave equations and Hamiltonians and all kinds of high-level math that we're not going to get into. But essentially, when we describe where electrons are, we kind of start out maybe in middle school, high school, when you learn that protons and neutrons are in the nucleus, electrons are orbiting around the nucleus. We start out thinking, well, maybe it's like the solar system where the planets are moving around the sun. And at first you might think they're circular orbits, and then you find out they're actually elliptical orbits. And then with this, we start out thinking that the electrons we move around the nucleus kind of like that, but actually electrons are moving randomly around the nucleus. They do not follow a circular or elliptical path. So Schrodinger derived mathematical equations to calculate the probability of finding an electron in a given region around the nucleus. So when we talk about orbitals in this class, we are talking about basically a region around the nucleus, and sometimes we refer to it as like the electron cloud, and it's just the area around the nucleus where we think we would find an electron. When we draw an orbital, the darker the shading is, the higher the probability that the electron will be in that location. And then as the shading gets lighter, that means the probability is going down of finding an electron there, okay? So this drawing is for an s orbital, which later we're going to draw it as a sphere or a ball, and it's going to look like a hard shell, but when we draw it that way, that is not very accurate. This is what an s orbital should look like, okay? It's a cloud that kind of becomes more diffuse as you move away from the nucleus, meaning the electron is highly likely to be in this region here. It is not as likely to be further out, okay? So just keep in mind, orbitals are not like hard shells. They're not real things. We're just trying to calculate where are we most likely to find an electron, okay? The equations that we use are going to give us several different shapes. The simplest shape is more of a spherical shape like the s orbital, so that's our first type of orbital that we're going to see. But then the other ones that we come up with are going to have more random or weird shapes that we'll see. Okay? So our s orbitals, now when we derive these, the mathematical equations, and if you've taken calculus, you can derive the equation of a line. The formula is y equals mx plus b. You can derive the equation of a circle. I think that's x squared plus y squared equals 1 is the unit circle. You can derive the equation of a parabola or a hyperbola. You can derive the equation of a sphere. You can derive the equation of a coffee cup. Like you could derive an equation that describes the shape of a coffee cup, okay? So mathematicians come up with these equations to describe a region of space. So s orbital should look like that, but we can make different sizes. So the first s orbital, probably this s orbital, a lot of times we're going to draw it like this. And then as we start calculating where electrons can go, as we go, we're going to use the same shape several times, but each time we use it, it's going to get bigger. So if I have an atom, I could put some electrons in the first shell s orbital, so I'm going to call that the 1s orbital. But then later I'm going to come back and say, okay, well, if I go further out from the nucleus, I'm going to use that same shape again. It's bigger, it's going to be a larger cloud, but now there's going to be a second shell s orbital. And then later I'm going to come back and say, okay, well, now I'm going to have a third shell s orbital, okay? Now, each time I say the word shell, I'm referring to like the next level out in terms of energy. The electrons close to the nucleus are going to have the lowest energy. The further out from the nucleus we go, the energy is going to increase. So we're going to have a set of orbitals in the first shell, and then another set of orbitals in the second shell, and then another set of orbitals in the third shell, and then keep going further and further out. Each time we go to a new shell, since it's bigger, we're going to be able to put more orbitals and more electrons inside that shell. Okay? So, at that point, let's just look at our shapes, and then I'll cut off the video. So I've got my s orbitals. So, again, you can mathematically, the top graphs are just showing how far out the electrons are. So I've got my first shell, s orbital, and then I've got my 1s orbital in the middle, and then if I go further out, I've got my second s orbital. So it's kind of another sphere around the first one, and then to finally have the third one. So I've got 1s, then 2s, then 3s, further out from the center of the atom. So those graphs are kind of showing where you're likely to find electrons for each one of those. But then mathematically, other than s orbitals, we also have p orbitals. Again, the true picture of a p orbital should look like this, where it's a cloud of high probability. If an electron's in a p orbital, it has a high probability of being here, it has a high probability of being here, but actually in the center, there's a plane that cuts through the middle right there. That's called a node, N-O-D-E, and it's a place where there's a 0 probability of finding an electron. So essentially, the probability of an electron crossing between the bottom and the top, the electron cannot pass in between those 2 points. There's an area of 0 probability in between. But the funny thing is, electrons do jump from here. They can jump up here anytime they want to. So somehow, and this is where quantum mechanics just really gets weird, somehow the electron can exist down here. It can also exist up here because this is one orbital. So electron can be in either position. This is one orbital the electron can be in. But somehow it cannot pass through that middle point. But yet it does. Okay? Now, when we do math, sometimes we do calculations, and if you remember the quadratic equation, negative b plus or minus the square root of b squared minus 4ac all over 2a. So that equation, when you solve the math for that equation, you get 2 answers. And both answers are correct. Okay? Well, mathematically, when a physicist derives the equation for a p orbital, he gets 3 solutions, or she gets 3 solutions to the equation. Okay? They are oriented on, they are perpendicular or orthogonal to each other. So if we decide to put one of the p orbitals that we get on an axis, say the x-axis, the other 2, I'm going to get one on the x-axis, one on the y-axis, and one on the z-axis. Essentially, they're all going to be 90 degrees from each other. Each one looks like this in reality, but it's easier to draw it as a hard shape. So this orbital is normally drawn like this, but then I also have one perpendicular on the x-axis and one on the y-axis. Okay? So p orbitals always come as a set of 3. Whenever we derive orbitals, each orbital individually can hold 2 electrons. So I can put 2 electrons in this one, I can put 2 electrons in this one, I can put 2 electrons in this one. So a set of p orbitals will hold 6 electrons. Our next set, and again the mathematical, there's a pattern. S orbitals in each shell, I only get 1 s orbital. When I get p orbitals, I always get 3 of them. The next type of orbital are d orbitals, and they always come as a set of 5. So I get 5 d orbitals. They look a little bit like the p orbitals, but it's just that we're doubling them. Instead of having one dumbbell shape orbital, now we're going to take 2 of them and cross them. So I have 4 different variations that are just in different planes geometrically. And then the 5th one is weird. It's actually like a dumbbell with a donut around it. Again, all you have to be able to do is recognize the shape of these. If I showed you a picture of one of these orbitals and asked you what type of orbital it is, I would expect you to tell me if it's an s orbital, a p orbital, a d orbital, or our last option are f orbitals. Okay? And so the elements that exist on Earth, and we go up to element 118 is how many have either exist on Earth or have been produced in a lab. The only orbitals that we use are S, P, D, and F. Okay? Now theoretically, if a scientist is able to produce a bigger atom than what we've produced before, we would eventually get to, again, orbitals are just mathematical calculations for where an electron should go, like where it should exist. We could derive orbitals that for atoms that are bigger that don't exist yet, but we can still tell where the electrons would be if we created those elements, okay? So up to this point, we've only put electrons in s, p, d, and f orbitals. Later on, we can theoretically predict there could be g orbitals or h orbitals or I orbitals. It would follow the same pattern where s orbital always comes by itself, just one s orbital at a time. The p orbitals always come as a set of 3. The d's come as a set of 5. And finally, the f orbitals, as you can see, there are 7 f orbitals that come at once. If I have one f orbital, I get 7. They come as a group, they're a package deal. Okay? So those are all our orbitals. We'll get into the quantum numbers that define those later. I'm going to cut off for now, but we're going to get into electron configurations as our next topic.